So far, we presumed the spatial probability distribution was steady in time. But quantum mechanics must model situations that are not stationary. Indeed, we just looked at the harmonic oscillator problem and found states that were not changing in time. The spatial probability distribution was fixed in the energy eigensolutions we found. There was no apparent evidence of any oscillation. Even when we're in the higher energy eigenstates, when for sure there was energy in the oscillator, nothing is apparently oscillating. Of course, the correspondence principle is telling us we had better find some way of explaining the behavior of oscillating systems because classically, again for sure, we know we can make such simple harmonic oscillators oscillate. A key point is that so far we've only looked at energy eigenstates. In fact, as will become clear, these energy eigenstates have the special property that indeed nothing measurable in them changes in time. To understand systems that do change in time, we need to go beyond the idea of energy eigenstates, indeed beyond even the idea of eigenequations. But we have to do this in a way that connects back to our time-independent Schrödinger equation and the perfectly valid solutions we've found to that. The key here is that we need the time-dependent version of the Schrödinger equation. So here we're going to rationalize a time-dependent version of Schrödinger's equation. An important point about it is that, perhaps surprisingly, it's not like the classical wave equation in its mathematical form. Now, we will show how we can link this back to the time-independent version of Schrödinger's equation, of course, but then, more importantly, we will show how to describe time-dependent behavior in quantum mechanics. Then we will introduce a very important concept in quantum mechanics, which is superposition states. Now, perhaps we have so far only encountered these in discussions such as Schrödinger's cat, which may make them seem bizarre. In fact, superposition states are essential for understanding time evolution in quantum mechanics. They also make that time evolution very easy to calculate.